Thanks, Stephanie, for the introduction. So yes, you've seen 15 years in South Africa, 11 years in Australia, coming from France, the accent never dies. So for the next 40 minutes, you're gonna have to suffer it. The talk today will be introducing what we call the MAG ASSEGAI program. This is basically a collaboration between the Wits University and the University of Free State with equipment which we're making available as Excision coleopter. Try to find out. Here we are. So that disclaimer, don't worry. You just agreed that you're gonna suffer 40 minutes with my accent. That's the only things you agreed. That's a summary of a talk. I think the talk will be available somewhere so everybody can download it. That's myself. I'm going too fast. Yes, in airborne geophysics, you have four main components to consider. The first one is a carrier. There's the one that's going to transport the sensors, and the sensors are the one we're going to do the measurements of the information that you really need. As far as the carrier is concerned, and also the sensors to some extent, they're just a means to an end. You don't really bother too much about it. They need to do the job. The last two components of your equation is the data that you acquire, and it's to be useful, obviously. And the ultimate important information parameters is the information and the knowledge that you extract from the data. Now, obviously, today I'm going to focus a lot more on the carrier and the sensors, and obviously that machines here, which we're making available to the university, and which many of you will certainly use via various projects. What you have here is a bit of an aperçu of what is airborne geophysics yesterday and nowadays, with various big aircraft. So these are not UAVs, they are manned aircraft, the traditional aviation, which has been used for the past 50 years, sorry. And that some of them are still flying. Then you had, for the past 15 years, a lot of innovators, and some of them here were the first light aircraft flying from Edcon. You have bigger business with the Zeppelin flying in Botswana for the Bears at the time. At the bottom, you have gyrocopters. This is something I've been developing here in South Africa for 10 years, up to a couple of years ago. And obviously here, the UAVs. At the time of Fugro, that was one of the first UAV MAG system, the Geo Rangers, which is no longer in use. So that was a bit of the innovators, pushing the boundaries in flying objects, trying to measure geophysics. But today, tomorrow is, in terms of manned aircraft, it's the use of light sport aircraft. The one here at the bottom, which was one of the aircraft we had here in South Africa. And the future is coming towards more of a now light sport aircraft, which are also certified. I'm not going to go further on that. In the traditional aviation, if you don't have an aircraft certified, it's still experimental. It's a lot of trouble. I went through that. I know what I'm talking about there. That machine at the bottom is still experimental. It's wonderful, but it's a lot of problem to operate, at least beyond the South African borders. But I'm going to focus, and then the future. At the top, probably one of those flying car will come to reality at some stage. And some of you starting your career might fly from home to the office, meaning the airport, and take off for some magnetic surveys. It's going to happen. At the bottom, you have certainly the future UAVs, which have a long autonomy, long-range UAVs, which are right now more military-grade machines, and which will one day take more of a fly from the manned machine. But that's the future. It's still not easy to operate right now. At the bottom, you have here a former CH-3 combat machine that was retrofitted for MAG surveys in Zambia for the government. So it's going to happen sometime. And ultimately, one specialty of a human species on mimicking the nature, you will have very small hummingbird machine, which will ultimately carry also sensors if we can reduce their size and their weight to something that can be carried by a small robot. So that's for the aperture of the airborne geophysics and the future, as I see it also. And what I'm going to do now for the next few slides is to talk more about MAG ASSEGAI. It's the name that was given of a program. It's a South African unique program for drone magnetic platform, and it's a collaborative program, which is a machine the closest to be there. Says that Wits, which you can use on many of your projects. That was brought by both universities, Wits and UFS, and we as providing the machine and will support the project when if needed. The point of contact for those who are interested from both universities, if you are interested in specific project, and that goes towards inviting other universities, which I think is the idea behind the program from Wits and UFS. Let's look at a bit of an aperture of the UAV industry. Basically, the UAV has taken up more and more space for application with the 3G and the 4G, allowing better communication. And that's where we stand now. And with the 3G coming in, the 5G coming in, we're going to start to see some new application over the next 10 to 15 years. And that means about swarm drone. And we'll have to think about what is really useful for geophysics or not. But then you're going to have also a lot of application, and one of the major one will be autonomous UAV, meaning that machine taking off on its own and monitored by someone at 1,000 kilometers. This is where we're going. It's already there, actually. It's feasible. That's just there's some issues with regulation, but it's where we're going. Commercial drones have been taking off for the last 10 years, 5 years, and what you have is here, you see that's 12.6 billion US dollar spent in terms of revenues, and 2.6 million drones, over 2 million drones sold, and that is only for the civilian market. We're not talking about the military. We don't really know what they're doing, and we might not want to know. The applications, essentially, then you have a diagram, but most of the UAV applications are really focused about visual inspection of assets and infrastructures, power line, and this kind of. That's the measure work of the UAVs. Geophysics in there doesn't really show up yet. It's going to come in terms of mapping, simply because most of the sensors were not yet the size we can put on a small UAV. And when you have to use a bigger one, there's always a lot of problems. So this is mainly right now a lot of inspection, and there's also the transportation, which is slowly growing. But soon, mapping will also become one of the major applications of UAV. With UAV comes also a certain number of threats and risk to the UAV, but also to us people. And then there's an aperture of what's happened, but you have some malicious communication. It's basically hacking the video of a machine. This is happening. Spoof signals, which basically you derive a drone toward the wrong direction for whatever nefarious purpose. The controlling of a signal, the UAV can be taken control by third parties. Signal jamming, which is one that is developing a lot, so that police force can control or remove those threats from where they shouldn't be. And that's a couple of threats which are important because they provide a lot of restriction on how we can use those UAVs for the application we want, and particularly in exploration. Let's see, when do we need a drone? Now, to assess what carrier you need and when it's flying, the drones versus a manned aircraft, you have to consider three parameters: the operations difficulties of the machine, the resolution of a signal strength that you're looking for, and the coverage. And you see that the manned aircraft is really in that domain. At the bottom, you have all the ground surveys. The UAV is frequently and wrongly put as a competition of an helicopter survey, manned machine. And that's a bit of a mistake and what we learn as from experience. And that's the red zone. There is more where the drones is really operating. And it's more a competition or a replacement of ground geophysics and a ground crew. It's slightly overlap a bit with the flying windows of helicopters, but it's a very big mistake to think that UAVs, small UAVs particularly, like this one, will replace manned machine. That's a reality we learned from operations, but from costing. I'll get back to that later, because I'm sure you will heard that this one, and it looks easy, it's simple, it's cheap. This is not the case, and I'll show you that later. UAV classification, I'm not going to go through that a lot, but there's a lot of tiers. The tiers 1 to 5, 4 are basically military machines and atmospheric level studies. The one that we concern for in geophysics is small and macro UAVs. This is the one you have on the table here today. You have two types of UAV, small and macro, a rotary wing and a fixed wing. That's very similar to the manned aircraft situation. And you have a special category, which is more on the airship and the blimp. They obviously also are unmanned machines. There you have some developments of this blimp there, not the Zeppelin, they're a lot smaller, but they're still 15 to 20 meters long, and they were mounted here with a magnetometer. Now, we're not going to talk about that today. Those machines don't have much of a future in the sense that they're very sensitive to wind. And so you better stay with the other UAVs. Now, in that category of UAVs, between the fixed wing and the rotary wings, you have also hybrids. And that's basically a machine that is as a shape of a fixed wing, but takeoffs and land vertically. It's what we call the VTOL. I use the term during the talk, vertical takeoff and landing. It's just that when you want to use a fixed wing UAVs, you have to basically, or you have a landing gear and all the engineering problems that comes with it to take off and land. Usually most of the UAV get catapults, but once they're in the air, they need to land again, and they usually land on the stomach, on the grass or whatever. That's a bit of an issue when you have expensive sensors in it. So it's why then the VTOL has developed a lot. And then on the rotary wings machines, you'll have this type of bigger machine. These are unmanned small helicopters, which can carry up to 15 kilometers. You see these ones have a MAG on either side here. They are a lot bigger than the small UAVs and a little bit more difficult to operate and expensive. And at the end of the spectrum, you have the multi-rotor, and then you have hundreds of it, different colors, and you have octocopter, hexacopter, quadcopter, depending on the number of rotor which you get here on the top. And the more you have, the more payload you can catch or pull up, and the more stability you might have. What are the key features? For a fixed wing, it's obviously high speed and long endurance. This is what you would like to have to cover as much ground as possible. The fixed wing hybrid, this one here, have a long endurance and a VTOL characteristic, which allows it to not have to get a landing gear or use a catapult. The single rotor will have long endurance, hovering, and a VTOL. The multi-rotor, the one we have here, and the one you have now at the university, will have a shorter endurance, but still have a capacity of a VTOL and hovering and slow speed. Remember, in geophysics, you want to fly slow and low, and that's why those machines are quite interesting. That's a diagram showing over the past 10, 15 years. In blue, these are the fixed-wing UAVs. In orange are the helicopter. And what you see in gray here is it's a big burst 2 or 3 years ago on the use of this multicopter, just because they are easier to operate, definitely, and they can allow you to do a lot more than many of the other machines. Now, an important part. There's one big thing that you have to think every time you operate a UAV. Are you legal or not? I can tell you there's a lot of cowboys out there. And I'm going to show you a bit what is needed to operate a UAV legally, not only to be legal for the point of being legal, but also to keep you out of jail. drone laws are constantly changing and evolving. It's still a young domain for the aviation. It obviously takes advantage of a lot of the manned aviation experience. But so when you want to fly a UAV, particularly if you want to go out of your home country, check where you are, check a website. I've given here just a website, which is a UAV system, which compile regularly UAV regulation everywhere in the world. Go and have a look at that first. Now, today I'm going to focus on our civil aviation here in South Africa, and I'm going to show you a bit what do you need to do to operate legally UAVs here in South Africa. Here you have a table which shows you different corporate environment for private use, and then the non-profit operation, corporate operations, and the commercial operations, and all the requirements, yes or no, about a couple of key regulation and authorization you need to get. There is two important things you need to obtain is what we call ROC, which is the remote operating certificate. And the second one is the RPL, the remote pilot license. Unless you only use your drone for private purposes, you cannot operate it without an ROC or an RPL if you do any type of activities that would basically generate an income. Imagine you do a video with the private purposes on the beach, you put it on YouTube, and you sell whatever, some kind of YouTube videos, you have generated an income. And if a CA look at that, they're gonna look at, okay, does that person has an ROC, an ROC and an RPL? If you don't have, you're gonna be in trouble with the authorities. Now, there's various situations there. Many people do that. It's a kind of catch me if you can game frequently, but often you get caught. There is, in Australia, for example, now there's a department at the civil aviation. There's people who just spend their time on internet to find who published what. They have now artificial intelligence, which will pick up keywords, and I will try to check against their list of authorized ROC. That is happening. I haven't heard it yet at civil aviation here, but don't make a guess. They're checking those things. Now, you have a small fish, private person, and you have a big one, the corporates who will try to get away. And they're chasing more of these ones. But you need to be aware of that. And they need to police that domain. Why? And I'm myself happy with that, because it impacts us. When cowboys are around there, it makes the regulation more and more complicated, and I'll show you some of them. And then our jobs and trying to develop airborne UAV geophysics is becoming more and more complex and a bit of a frustration. So you see what I said earlier, as long as you fly on a beach, take photos of a family or whatever, it's a private use, you don't need a pilot license and you don't need an operating certificate. Beyond that, as soon as you do surveys for generating an income, whichever it is, then you need an ROC and an RPL. I'm going to tell you now. Now, 10 years ago, you couldn't, if you wanted to fly a UAV, you needed to have your own ROC. That means minimum 12 months and hundreds of thousands of rounds. It was very expensive. It was a limitation. Now the law has evolved and they allowed what we call RC onboarding. So if you're a pilot, you got your license, and I'll get to the details now, you can just buy a subscription to someone who has already an ROC, which you can use as an umbrella. That's an evolution of a regulation that helps to make the use of UAVs a little bit easier. Let's look at what it costs. An ROC onboarding. As I said, if you want to get your own ROC, 10 years ago, 5 years ago here, it was 12 months, a little bit more than that usually, and hundreds of thousands rand. Nowadays, it's 24 months. So it's a long time to set an ROC. And now, when you set an ROC, you also need to have a certain amount of people employed, which are the chief pilot, the maintenance compliance person. So it's a real business. So it's why the onboarding has now helped a lot of pilots who wants to do something with their license. And so the onboarding cost a once-off 12,500 rand. That's administration fees. And then it's 7,500 rand a month. Roughly for a year, it would take you just over 100,000 rand to have access to an ROC. And every year you have to renew it. And that's 90,000 rand roughly. That's numbers from presently. As a pilot license, the RPL, your license, if you want to pass your license, roughly in South Africa, it's 55,000 rand as a once-off, and then you have some travel. Remember, as part of a license, you're going to have theory and practical tests to do. There's only a few centers in South Africa, so this means if you're in Joburg or Cape Town, it's good for you. If you're elsewhere, you need to travel. And the license will take you a good 3 weeks cumulated work. So you can start to see what it involves in terms of cost also. So roughly 65,000 rand, it's an estimate of what it costs to pass your license to be able to fly UAVs legally. Unless it's private use, again. Then every 2 years, you have to renew what you call your medicals. They want to be sure, but you didn't turn blind, you know, after 2 years, after your first license, that you can still see your UAVs. That's one thing. So every year, every 2 years is 12,000 rand. And then you have your pilot license, you still need to buy your subscription or to operate under the ROC. And that is another 100,000 rand a year. That's what it costs. So at the end of the day, to get started, you have to put 270,000 rand on the table. And then every year is roughly 186. They're big numbers, but it will keep you out of jail. I'll give you an example. Take your UAV up, you crash it. That's a law of gravity for the geophysics students there. Everything that flies has to go down at some stage. So if it crashes, it burns half of Gauteng, well, you have an insurance, it's fine. If you kill someone, or the fire kills someone, it's a criminal case and it's manslaughter. And that's will get you into jail. Now, these are the risks, things you need to think about when you operate UAVs. That's for the regulation and the cost. Now, there's a couple of things about UAVs, of do's and don't do's. They are more or less the same in every country regulation in general. They might change a bit here and there, but you never fly your UAV above or less than 5 meters for a group of people. Now, imagine that restrictions, it's always someone walking somewhere, so if you fly above it, at some stage you've been illegal. But you don't fly over property without permissions. That's a big thing. A lot of people think they can take off because they got their RC and RPL sorted. They can fly. No. You will have somewhere someone with a gun who will try to shoot down the UAV. It's not easy, but they're good shooters, they can make it. Now there's, unless approved by SACWA, Civil Aviation of South Africa, sorry, you cannot fly your UAV near an aircraft. You cannot fly 10 kilometers or closer to an airport. Your UAV needs to weigh no more than 7 kilos. That's really that for most of the rules. The big thing in UAVs, you'll have to remember, and if any UAV is above 25 kilos, then you are entering in a military grade machine. So then try to stay below 25 kilos. You cannot fly in controlled airspace, restricted airspace, and always prohibited airspace, meaning military camp, nuclear plants, all these kind of things. Makes sense, but you might be surprised at how many people get caught where they shouldn't be. Not flying higher than 150 feet. And then the big thing is beyond the flying a UAVs, the regulation is you have to fly with line of sight. You must always be able to see your drone. Flying beyond line of sight is something that is authorized on special case by the civil aviation in many jurisdictions. And that's a big thing. As soon as if you let your UAV going behind your line of sight, then you are illegal. And it's also a big risk. If you don't see where it is, you don't see what it does. There is training for flying beyond line of sight. My colleague Francis is an expert of that. He's trained and he's certified in France to do this behind line of sight flying. But despite having 20,000 kilometers of flying surveys and 2,000 hours of UAV experience, certified French pilot, they cannot fly here. The civil aviation will tell you, get out of my face. And that happens in many destinations when you are regulation. They force people to have a local license, which is one of the big limitations. Let's move on to, and the things we can do. So you must fly your drone with your line of sight, as I said earlier. Operate the drone in a safe manner. That all make common sense. And also inspect your drone. Even a small drone, like the second one on the side, a small Mavic, just inspect it, or you're going to have surprise. Now, looking at some limitation of UAVs. The weather is obviously a problem, particularly the wind. Site access. Well, if you have to fly in a line of sight and you're in the middle of a zone where you cannot get access, then you cannot get it. The size of a survey, interestingly, for these small UAVs, small and macros, a typical maximum size of a survey is 4 by 4 kilometers. Don't try to fly bigger than that. It's cheaper to take an helicopter. I had many surveys when it happens. Clients come to us and I want to fly my 10 by 15 kilometers and you take an helicopter. I don't believe it. And then when I see the cost, because you have to get access. Your 10 by 10 kilometers, you cast it in a small block of 4 by 4 kilometers. You have to move from one spot to another one, to another one, to another one. It takes a lot of time, it takes a lot of money in terms of labor and access. So think about this. A UAV, a small UAV like that, not talking about a bigger one, 4 by 4 kilometers is your typical size of a survey area. Where do I stand? Yes, the topography is obviously a limitation. Vertical obstacle, trees is a big problem. We have giraffe also in South Africa, which we have to take care of. The flight characteristic, the autonomy. The machine you have here is a bit of an older one, but it has still 15 minutes autonomies. The one behind, the small one, has half an hour or a bit more, 45 minutes. So UAVs evolved. And actually, your UAVs are like a laptop. Once you buy one, the next day is outdated. I just put it that way. It moves very quickly. But autonomy gets also improved. Small payload. Most of the UAVs will not be able to carry more than 5 kilos. And so it means that some sensors are too heavy and we can't take them on these small UAVs. The restriction, sorry. I said it earlier, 25 kilos maximum takeoff. The visual line of sight, that is an annoyance, but we have to deal with. You cannot do night operations. You cannot fly over people. And in some area where you have sparse population, well, you might not be able to fly in all area just because there is a couple of houses, there's a couple of people around. So technically, you're taking too much risk of flying over those areas. And certified unmanned aircraft pilot. Again, one of the big restrictions is that not a foreign pilot can come here and fly. He doesn't have a local license. Same thing in other destinations. It's not the case with traditional aviation where a foreign pilot can come here, apply for special authorization, and his license is recognized, and then they can fly. But the benefits of a UAVs is just easier access, higher data resolutions. You can fly slower, closer to the ground. The faster and cheaper is a bit of a myth. You'll be surprised. But any surveys that will take you more than a week, rent an helicopter. And I'm talking about MAG survey. And that's coming from my own experience. It's a safer versus low risk. UAV is not necessarily safer. You need to look at the risk profile, as I mentioned earlier, about fires and eventually killing people. They can operate remotely, which is obviously one of the major benefits of a UAV, and a quicker deployment to site. Put it in a backpack or in a suitcase, and then you can go straight to a survey area instead of waiting for an aircraft to take a week to cross Africa. Let's go on to now some example of geophysics technologies. Electromagnetic is already a tool that is used by here. It's octocopter. That was a nice slide I picked up from drone geoscience. And I put those things just to show you the tool. Here is the M61. The UAV geophysics gamma ray is also there, albeit some of those sensors are quite heavy. Now we're talking about 6 to 8 kilos as the minimum weight for a gamma spectrometric system. Here you have the Medusa, and here it's the Terra+ system, whichever. They're still big or still heavy, not necessarily big now. And so won't be able to be carried by that UAVs. You need something a little bit bigger. But it's there. Gravity, then what you have here at the top, that's where we started in gravity, that was 650 kilos. Then we moved to 150. Then we have a modern UAV, the modern, gravimeter with a GT here and the Centrex technologies, which are 55 kilos. Still, they're way too heavy for smaller drone to operate. But things are coming via the INS. You have here a German company, IMA Navigation. That is gravity made out of inertial navigation system. That is the size of a shoebox. And it's equivalent here, which we busy us working on with a CNRS. It's, you see the size, 2 tons, and we put it on a small UAV, the second one there towards the wall. And you start to get something like 2 milligauss. It's getting seriously, so that it's an inertial navigation system, so it's a lot of data processing. And then you have an example of things I've seen a couple of years ago. That was Glasgow University. They were using MEMS and basically it's things you have in your cell phone, and they were able to measure the tidal gravity. So there's things ongoing to maybe have a gravity on a UAV one day. Now let's focus on MAG. There is 2 philosophy in MAG, and it depends on the type of sensors you use. You have cesium or potassium sensors, which have a traditional best accuracy and magnetic sensors, but they're heavier and they are very sensitive to noise. And it's why you use them towed below the helicopter. That has in itself a lot of issues when your sensors catch a tree or whatever. Right now in South Africa, it is not legal to fly a towed bird unless you get a special authorization. The rule says that you cannot fly it. You have to apply for special authorization. You have 1 or 2 companies doing that, and they must have obtained their special authorization. And that's something to keep in mind. You can buy the tool quickly, but just check over time. You can use it and operate it as you want it, particularly here to be towed. Now, us many years ago, we moved towards the first gate sensors. Now, what you have here on the right is the machine that you have now at the university. We moved from the towed system because of safety, but also because when you want to use the cesium sensors, it needs to be corrected. Or we talk about compensation, and it's usually a big black box. But to do that correction, you use a first gate sensor. So you have 2 magnetometers. Now we just removed the expensive ones and started to work with a first gate. And that is MAG ASSEGAI last weekend. So you see at the top, the magnetic sensors is here. When you take off with the horizontal, and then when we are in the air, we start to pull it down so that the sensor stays away from most of the magnetic noise, or electromagnetic noise from the rotor and electronics at the top. And at the bottom here, you see my colleague Francis and Martin Clark from the University of Free State, the pilot of a program, which is their own training there. And you have here the team happy, Sue, Stephanie, Martin, the UAV, and Francis here after completing the whole weekends of training and flying. And then you have here Martin going solo for his first flight after getting the stamp from my colleague Francis. We can go home back to France and do whatever you want here. I just don't know what time I have there. If I enter in the details, oh, I'm gonna run out of time. I'm gonna skip a couple of things then about Inton versus Fluxet versus some case studies to show you some example. You have here a first survey flown with that machine just a little bit north of the Wits quarry, which is a place where you regularly go, I understand, to do some testing. And so you have this data set that is still under processing, and something that was processed, overly processed, and then showing that we flew two grids there. Here it was 20-meter line spacing, and then inside here we flew a smaller grid, a higher resolution at 10-meter line spacing. So this data is still being worked out, but that's one of the surveys that has been flown already with us. Not that machine, with a similar one. Again, the machine you have here at Wits was flown in Australia on a survey. On the left here, you have a ground magnetic data, quad at the mine. And on the right-hand side, you have UAV-borne magnetic data acquired at 15 meters above the ground. And in the middle here, you have the ground data upward continued to 15 meters, comparing basically the airborne surveys with against the ground data, just as a proof of concept. Yes, sir. Yeah. Now this is, in that case, the mine had a lot of high resolution, high frequency noise at the surface, and I wanted to get rid of it. So we flew at 15 meters, and we're just comparing to show that the UAV mag works. Now, the last thing I wanted to pass, it's a presentation I did some time. We all focus about mineral exploration. That's something that we don't do much yet. It's precision agriculture with geophysics. And that I think is something that should grow more. Myself, I'm convinced, and I've been doing a lot with manned aircraft. The UAV is opening the doors for this geophysics being applied to precision agriculture and soil mapping application. You have here a survey flown in Potchefstroom or close to Potchefstroom. So that wasn't done with a UAV. Show you, but data is a data. What you have here is we were trying to extract magnetic susceptibilities, which many agronomists want or would like to have. Now, it's not an easy game in geophysics, but what you have here, it's a two crop farm. This big anomaly is an underground pipeline. Farmer didn't even know about it. When we saw it, we had problems, and now you found the two hands now. So, and I understand that he's busy reusing it. Okay, so on that one, we were trying to see. So first, we have to do some upward continuation, trying to filter out that pipeline as much as we can. When we extracted the magnetic susceptibility, we can still see the pipeline. Obviously, it's a big anomaly. And we applied a directional filter, trying to remove the signatures of a pipe. You see that some of it is disappeared. We have a fair amount of information which should still be related to geology at depth. It's a very interesting research project or topics. It's trying to extrapolate magnetic susceptibility from high resolution UAV magnetic data. That was just something we did, we were trying. We haven't pushed it, but it's something very interesting to do because many soil agronomists and soil scientists, we will look for that information if we can provide it to them. The rest is gamma. What is important is not, so it's a bigger system, which you won't be able to carry there. I just wanted to show what we can do with gamma. Gamma, it's a technology we use to do geological mapping in general. Now, on that farm, what you have here, it's the equivalent thorium map. The clay percentage that was measured on ground samples, soil samples, just to show kind of a qualitative correspondence between the two. The same thing for the total count, that is inversely related to the soil sand percentage measured as a lab in a lab chemical analysis. And the same thing for the airborne equivalent potassium compared to soil potassium. That is a PhD work that is finishing at the University of Northwest, based out of an airborne small gyrocopters data set, which we had. But we do have a gamma spectrometer. We would need a bigger machine, but our discussion the past few days making me comfortable that we might be able to bring it here, and we could fly with things here under the MAG ASSEGAI program. We will discuss on these things, because combining both MAG and gamma is obviously the best recipes for exploration, but it's also the ultimate recipe for the agriculture. I'm going to skip that. I'm going to give you that one, the same area. Out of your gamma data, you can recalculate the dose rate. Now, what you can see here on the dose rate is, I don't know if you're familiar with that, but it's a measure of the amount of gamma ray radiation, which are expected to be absorbed by humans around in an area. Now, this is regulated. You're not supposed to be exposed to more than 1 millisievert. Now, if you look at here in the scale, that field is way above 1.2 millisievert. That produced a lot of crop. I have to ask the question, well, what do we hit? Now, that's one point. The second one I wanted to show, yes, is that. What we were able to measure, there's 2 directions in the high anomalies here of the dose rate. And we see 2 directions. And what we see also, well, these 2 directions change here. There seems to form S structures that you would see in structural geology. And these are the 2 directions in time that were used for plowing the field. That is very interesting how a high resolution gamma survey could show that kind of details. And talking with the farmers, he was telling us that the last owners was indeed plowing his field on that direction. So along the time, while plowing his field, he's moving all the particles regularly, every year and year on year. And then you can measure that. And that was flown at 15 meters above the ground with a small aircraft. It's the same thing that could be flown with a slightly bigger UAV with a gamma spectrometer. So that's the kind of application we have of our precision agriculture, which would be quick for geophysicists to do. I'm going to skip that. Yes, I'm going to focus on that one. This is interesting. What you have here at the bottom is nematodes. Who don't know what nematodes? They are small worms in the ground. And you have the good guys and the bad guys. Some will eat fungi, will release nitrogen, which is an intake for the plant and the crop to grow. These are the good guys, even if they look ugly. But then you have these guys, they are predators. This part is a stillet, what gets out, and I use it to puncture prey over nematodes, or they will puncture the roots of the crops, and the crops dies. Now, soil agronomists will do systematically map of those creatures to find out where the troubles are coming on the farm. And those nematodes have specific environment in the soil which they prefer to live. This means moisture and other physical parameters, clay content, sand content. So things we can measure with geophysics. And what we were doing on that project here, these outlines are the soil zones which we were able to identify, and the color zones are the concentration of each of those nematodes. Qualitatively, there is interesting relationship, and it was a proof of concept on our side just to see, is there something to do? And yes, there is indeed something to do, and we could help quickly with geophysics to identify soil zones which might be more attractive or less attractive to specific species of nematodes. Now, what is interesting here, no longer talking only to geophysicists, talking to a soil specialist, you're talking to a biologist. took me a lot of time trying to understand marsupial and nematodes and talk to a biologist and trying to explain what is physics and how all these guys can meet together. But this is a very interesting, the project was very, very interesting, trying to get this cross specialties research and interaction. And obviously a problem that affects the precision agriculture. And the last 2 or 3 slides is maybe the future about data visualization. This you might know a screen, typical GeoSoft screen. You are visualizing in 3D something that is still 2D, 2D dimensions. Now, this is what we do nowadays. It's still better than what we had before, from the electric computers down to the punch card. So I think we shouldn't complain too much, but there is something better than we must do. And that for those who've seen Avatar movie, then this is what we would love to have, holographic projection. This is no longer science fiction. Company in Australia has, and there's a few now in the world, have these holographic tables. And you see on the right, people with Google to be able to look at the 3D models of a city. Now that is quite recent, a couple of years, and it's already almost outdated. It looks like a mini 3D room. I don't know if people have seen 3D room in a seismic. Then this is what you have. But nowadays, there's a lot more developing, something we're working on now with a partner. And what you have on the side is basically a Microsoft Oculus. It's a 3D goggle. But software that is now provided by Cleario. And you have here a geologist looking at the 3D models of one of the pit or structures at the mine. And that is real-time collaboration with people having the same softwares, goggles on 2 different or 3 different places in the world. This is existing now. We busy us to do our first geophysical image. Hopefully, I'll show something at Saga at the end of the year. So that's the future visualization, and it's not that far. And it's what we call the virtual reality 3D collaboration. So that's a tool that's going to come to our toolbox as geophysicists to better interact with the data. And then the autonomous. I mentioned it a little bit earlier. We're moving towards a world where drones will not need us anymore. Might be scary, some movies have been showing that, but the point is where we're going, particularly when you're far or in big remote area. And they will not need any human intervention except for the monitoring at thousands of kilometers. This is something we see already in the mining industries with trains which transport minerals from a mine down to the port, and that is controlled from by one man in the control room thousands and thousands of kilometers away. Now UAVs is getting there. I'll show you what's happening. For that to happen, you need what we call a nest or a docking station. This is one of the docking station of DJI. On the left is closed. Here it's open. Once it's open, the drone can take off. Now, the purpose of this nest is just to recharge the drone between each of these operations. And that can be controlled from distance. And that is a static context. And then obviously you have already the dynamic one. In Australia, you have someone who's now built a trailer. It is all solar powered, and in the middle they put here the DJI dock station. And they use it, essentially their services there is for visual inspections of mine infrastructure. They leave the trailer in a mine, and they leave it there for months, and they control it from wherever is based as a support, as a service to the miner in that case. This is where we're going with the autonomous, and then obviously you'll have to see how we fit the geophysics package and the sensors to still fix in the box. But that's another problem we'll look later. And here we are. Thank you very much for your attention.